Our next topic is optimization. What we're talking about here is trying to find the best way to do something. Usually, the best way to do something, to optimize something, means either you're trying to make something as large as possible or as small as possible. Suppose you're trying to do a task and you want it to be done in the most efficient way possible. Typically, that means the smallest amount of time, maybe with the smallest amount of resources or the smallest amount of energy input. So in that case, you're trying to find the smallest, the minimum value for something to occur. Or you might be trying to find the largest volume or the largest area you can enclose. You're trying to find the maximum. And so optimization deals with trying to find the maximum and the minimum. Now, one thing to recall is we want the absolute best way to do something. We're looking for absolute extrema, an absolute max or an absolute min. And so the extreme value theorem says if f of x is continuous on a closed interval and differentiable on the open interval, then there exists an absolute max and an absolute minimum. See if you can barely read that. If f of x is continuous on a closed interval, differentiable on the open interval, then there exists an absolute max and an absolute minimum. In order to know that we have an absolute maximum and an absolute minimum, the function must be defined on a closed interval. And you recall, to find the absolute maximum, we had to locate the critical values and then evaluate the function at not just the critical values, but also the endpoints of the interval. It is possible. It does not always occur. It does not frequently occur, but it is possible that the absolute maximum, absolute min, the optimal solution could be at one of the endpoints of the interval. And so when we're setting these problems up, we must be able to define on an open interval where the function is being defined. So here is a typical problem of this variety. In fact, this is a classic problem. Suppose we have a river and a rancher wants to build some pens for the cattle. And so we're going to build fence here, fence here, fence here, but leave it open at the river. We want the cattle to have access to the water here. All right? And let's suppose we want to subdivide this into, let's say, 4 equally sized pens. And let's suppose we have 2,400 feet of fence available. We have 2,400 feet of fence available. We want to build this structure with 2,400 feet of fence. Well, what are some options? This is just one possibility. We could use more and more of the 2,400 feet for these fences that are come out perpendicular to the water. But if you make these longer, what that means is you have less fence for the width, and so they become very long but very, very thin. So another possibility would be use less of the fence for these distances and use more of it for here. So another possibility is, this is one picture. One possibility is we could make these very, very long and very slender. Another possibility is they could be very wide. But I don't know. All right. question is, which of these gives the most possible surface area? We want to have the maximum surface area available for the cattle. And so this would give a different surface area than this region, which gives a different surface area from this region. We want to find the dimensions. So find the dimensions. Now, what does that mean? Let's call each one of these horizontal distances x, and each one of these vertical distances y. All right? We want to find the dimensions x and y such that, and we want the overall total surface area to be maximum. Total area is maximized. We want the maximum total surface area. All right? So, let me get rid of these pictures here. That's our problem. Now, the procedure, we'll talk through the procedure in general, and then we'll go through and do the specific problem here. The procedure is we need a function for the quantity to be maximized. What is it we're trying to maximize? In this case, we're trying to maximize area. In a different problem, you might be trying to maximize volume. You might be trying to maximize the number of items. In a maximized or minimized, it could be you're trying to minimize the cost. It could be you're trying to minimize the material used. It could be maybe in a different problem, you might be trying to minimize the amount of fencing used. Any problem can be approached, but whatever it is you're trying to maximize or minimize, you need a function for that. We need, in this case, we're trying to maximize area. We need an area function. So we need an area function. Now we'll do the details later, but this is the procedure. So you need a function for the quantity to be maximized. You need an interval over which that function is defined, and typically it needs to be a closed interval. We need a closed interval over which this function is defined. All right? Now, something to bear in mind is this. Imagine the values of y get larger and larger and larger and larger. That means the values of x's have to get smaller and smaller and smaller. Theoretically, and this is, I'll give you this, theoretically, the value of x could get very, very small. It could be only 2 inches wide, but very, very long. We could have pens that look like this. Now, that's not likely to be the actual solution in this particular case, but in principle, that's possible. As x gets smaller and smaller and smaller, theoretically, x could vanish to 0. And so when we find the interval over which this function is defined, we're talking about the limiting values. What is the limit? What is the smallest possible value that x could achieve? In this case, as these get thinner and thinner and thinner, x is getting closer and closer to 0. All right? So as typically in a problem of this variety, the smallest value of x we could allow is typically 0. Now, we'll talk later about how to find the other value, but one thing that's important to know is very often the theoretical smallest value possible, the endpoint of the interval, very often is 0. That is, in principle, a possible solution. And then, okay, so we'll talk later about how to find the specific value. But you have the function, you have the closed interval, and now you resort back to the work from a couple sections ago. You need to find the critical values and then evaluate, in this case, the function a at all the critical values and the endpoints. You must do endpoints and the critical values. You must evaluate the, in this case, the area function. At the endpoints, we know one of them is 0. We'll find the other pretty soon. Evaluate the area function at the endpoints and at the critical values. And since we're looking for the maximum, then you choose the maximum. So that's the procedure. Get a function, get an interval, find the critical values, evaluate the function at the critical values and the endpoints, and then choose the maximum. If this were a minimization problem, you would choose the minimum.